Welcome back to Aarambh Dev Hub. This is episode 2 of the Gupti series. In episode 1, we defined the product and architecture. Today we build the data layer, and this is one of the most important episodes for long-term maintainability. Most teams lose stability not because encryption is wrong, but because contracts are fuzzy. Inputs are loosely defined. Errors are inconsistent. Responses change shape unexpectedly. And front-end teams start patching around back-end behavior. We are not going to make those mistakes. Today we lock contracts properly from the start. Let us set the mindset first. A secure product needs secure logic. But secure logic depends on reliable data boundaries. If validation is weak, malicious input reaches deeper layers. If response shape is unstable, clients break silently. If domain model is mixed with API payload model, every refactor becomes risky. So this episode is about boundaries. We define request DTOs, response DTOs, domain model, error model, and config model. Once this is stable, implementing handlers becomes much easier. Because behavior is now constrained by clear structures. The data layer is the foundation everything else builds upon. Before we dive into the technical details, a quick reminder. If you are enjoying this series and learning something valuable, please subscribe to the channel and turn on notifications. Join our Discord community to discuss these concepts and ask questions. And if you want to support this work, check out my Buy Me a Coffee page. All links are in the description. Now let us continue. Our primary request is the create secret request. At minimum, it carries secret text. Optionally, it carries TTL seconds for how long the secret should live. Now the critical part is validation policy. Secret should not be empty. Secret should not exceed max allowed size, which we set at 1000 characters. TTL, when provided, should stay between allowed minimum of 60 seconds and maximum of 6400 seconds, which is 24 hours. Why validate here at the boundary? Because this is the entry gate of untrusted input. If we allow invalid data deeper into the system, later checks become inconsistent and scattered. Also, validator annotations make policy self-documenting. When another engineer reads the DTO file, they see allowed boundaries immediately. No guessing required. Now think about UX impact. If DTO validation is predictable, frontend can provide consistent feedback. No random 500 errors for user mistakes. The user sees clear validation messages. Another hidden win is testability. Validation boundaries can be unit tested independently from handlers. That gives quick feedback before integration tests even run. Let us go deeper into practical edge cases we care about. First edge case is empty or whitespace only secret. This should fail fast with a clear message. We do not accept secrets that are just spaces. Second edge case is oversized payload. If someone tries to send a 50 kilobyte secret, it should fail with a policy explanation, not a generic 500 error. Third edge case is TTL below minimum. Short TTL might sound safe, but inconsistent policy can create unreliable behavior. We enforce a minimum of 60 seconds. Fourth edge case is TTL above maximum. We block unrealistic values to avoid accidental long lifetime secrets sitting in memory forever. Fifth edge case is missing TTL. When no TTL is provided, it should default to a configured safe value, not undefined behavior. Our default is 3600 seconds, which is 1 hour. This is why data layer is not boring. It is where reliability is born. Every edge case you handle here is a bug you prevent in production. Now let us look at response DTOs. Create response should include slug, which is the unique identifier, full reveal URL so the user can share it directly, and expires at timestamp in ISO 8601 format. Reveal response should include the plaintext secret and created at timestamp so the user knows when it was created. Error response should include error message and an optional detail field for additional context. Notice what we avoid. We do not return internal storage fields by accident. We do not leak unnecessary metadata. We only return what UI and user flow truly need. This keeps API surface clean and predictable. Another important point is timestamp format. Using stable ISO-style serialization avoids parsing issues across different clients. Whether it is web browser, mobile app, or automation script, timestamps work consistently. When response contracts are stable, front-end complexity drops dramatically. Because UI logic can trust the shape and focus on user state, not schema guessing. Now the internal secret model. This model is backend only. It contains fields like encrypted data bytes, nonce bytes, key bytes, slug string, created at timestamp, and expires at timestamp. Why keep separate from DTO? Because domain needs and API needs change for different reasons. API needs might change due to UX decisions. Maybe we want to add a field to response. Domain needs might change due to storage or security decisions. Maybe we change encryption algorithm. If both are coupled in one struct, every change becomes high risk. You cannot touch one without affecting the other. Separation gives us controlled mapping. External contract remains stable while internals evolve safely. This is one of the best habits you can build early in any backend codebase. Separate what you expose from what you store internally. Now errors. This is where many projects collapse into chaos. Generic string errors everywhere. Inconsistent status codes. No reliable machine-readable responses. Frontend has to guess what went wrong. In Gupti, we define a typed error enum. Each variant represents one known failure class. Examples include outfailed for when the secret does not exist, expired for when the TTL passed, decryption failed for when something went wrong with crypto, validation for input errors, and internal for unexpected failures. Then we map each variant to explicit HTTP status and JSON body. Mounted returns 404. Expired returns 410 gone. Validation returns 422 unprocessable entity. Decryption failed and internal return 500. Why this matters so much? For frontend, it enables clear state branching. Different error codes trigger different UI behavior. For debugging, it provides clear log intent. You know exactly what failed. For future maintainers, there is one place to understand failure semantics. For product behavior, user sees meaningful feedback instead of confusion. Tight errors are not just clean code style. They are product quality infrastructure. Now config design. We define application config with defaults for default TTL seconds, max TTL seconds, max secret bytes, cleanup interval seconds, and rate limit per minute. Then environment variables can override these defaults. For loading environment variables from a .env file, we use the debov crate. At application startup, we call debov.bvolvic, which loads variables from a .env file in the project root. This is optional and gracefully handled if the file does not exist. The pattern is simple: debov for .env file loading, then std.env var for reading individual variables with fallback to defaults. This gives two immediate benefits. First, local developer can run the project quickly without complex environment setup. Just clone and run. Create a clrs.env file with your custom values or rely on sensible defaults. Second, deployment can change behavior without code edits. Different environments can have different TTL policies or rate limits. In production, you typically set environment variables directly rather than using clrs.env files. Good config design is about safe defaults and flexible override. That is exactly what we implement here with debov plus fallback defaults. Before we close, note what this episode enables for testing. Now we can test DTO boundary behavior, error response shape, status code mapping, timestamp format consistency, and config fallback behavior. All before heavy integration flow. That is a huge advantage when building reliable APIs. Quick recap of today. We built strict request and response contracts. We separated domain model from public DTOs. We implemented typed error semantics with proper HTTP status mapping. We finalized environment-driven config shape. Next episode is the crypto core. AES 256 GCM encryption and decryption lifecycle with safe failure behavior and memory hygiene after reveal. That wraps up episode 2 on data layer design. If this content is helping you build better Rust backends, subscribe to the channel and hit the notification bell. Join our Discord community to connect with fellow developers. And support this series on Buy Me a Coffee if you can. Links are all in the description below. Your support keeps this series going. See you in episode 3.